Okay, so let's get started. So let me recall a couple of concepts from analysis that you should know. So the first is uniform convergence. So you have a bunch of functions, right? And they're all let's say that they're on some set and complex value functions. So we say that f sub n converges to f uniformly. What does that mean? Can anybody remind us what uniform convergence is? Anybody remember? Justin?
Doesn't that mean like all epsilon works in the delta epsilon definition?
No, I mean not all epsilon works, but rather So convergence. Remember, convergence at a point would mean that given any epsilon, there's an n past which these guys are within epsilon of each other, right, at that one point. And then uniform convergence means that, go ahead, whoever you are.
I'm Noah.
Noah, yes.
It means that we pick the delta before we pick the points. So there has to be a delta that works at all points, right?
So you're thinking about uniform continuity, I think. So this is uniform.
I might be thinking about that. I'm sorry.
Yeah, uniform convergence. You just don't say delta. Instead of saying delta, you say n.
Oh, okay.
Right. That there's an n that works uniformly. Right. So given any delta, given any epsilon, right, there exists an n such that, right, if n is bigger than n, then, right, the distance between f sub n and f is smaller than epsilon, right, for all x in your set, right. So, right, you may have seen, it's something like, I'm drawing this in R, but, right, so here's your f, right. What it means is that, given some epsilon tube, right, there's an n beyond which all the graphs lie in that epsilon tube, right? Okay, a lot of people I don't recognize today, but okay. Okay, so that's uniform convergence. Next thing to recall, Weierstrass M-test. Anybody remember the Weierstrass M-test? Weierstrass M-test, anybody? So this is when you have, you've got a series, right? Right. You've got a series, right? And you're trying to show that series converges uniformly, and is that if there exists some bound, right, such that each of the functions is bounded by the m sub n's, and right, these m sub n's converge if you sum the bounds, then the bounds converge. Then you know that the series converges uniformly. Okay, I hope you've seen that before. If not, we're just, this is it. We're gonna use it. The root test. So you've got some sequence of complex. You've got some series of complex numbers, right? What does the root test tell you? Can anybody remember the root test? Sure. Yeah. Right. Just you look at the limit of the absolute values. You look at the lim sup of the absolute values of the nth roots, right? And as long as that is smaller than 1, so if this thing is smaller than 1, then you have convergence. Right? If it's greater than 1, then you have divergence. That's the root test, right? Okay. So those are things that hopefully you've seen before, and we're going to use them shortly. Okay, so the first thing that I'm going to put up, you've definitely seen before, is the definition of a power series. So any expansion of the form, summation a sub n z to the n, where the a sub n are constants, right? And the z is a complex variable. Anything of this form is called a power series, right? Power series, right? Right. If you have some function expressible as a power series, you say this function has a power series expansion, right? Like the theorem that's going to be useful for us is due to Abel. This is the theorem of Abel that given any power series, there exists an R, could be 0, could be infinity, such that if z is less than R, then the series converges absolutely. Right? If you're outside, of that disk, then the series diverges. Right, and further, so for any row that's smaller than R and greater than 0, greater than or equal to 0, we have uniform convergence. On the disk, on the closed disk of radius rho. Okay. Right. So this is what this is saying is that there's a radius of convergence, right? So you have your power series. You have your power series centered at 0. What this is saying is that there's going to be some radius, and within the disk centered at 0 of that radius, you've got absolute convergence inside here. You've got divergence outside the closed disk, and importantly, if you look at any disk inside here, then you've got uniform convergence on that closed disk. Okay, and the proof of this is simple. All you do is just use the root test, right? So you just say, well, look, right? So if we consider the power series, summation c sub n z to the n, then the root test tells you that if you look at the lim sup of the nth root of the nth term, you could look at that, right? And what you see is that you get the absolute value of z times the lim sup of the nth roots of the c sub n's, right? And right, so what the root test says is that you got says that as long as this thing is as long as if this thing is smaller than 1, then you've got absolute convergence, right? So this is your call this thing alpha, right? It's saying that as long as absolute value of z is less than 1 over alpha, then you've got absolute convergence. If it's greater than 1 over alpha, then you've got divergence, right? So this is the radius, right? This 1 over alpha is the radius, right? So that's the result of that part. The formula for the radius is due to Cauchy Goursat. Okay. So yeah, so that that's pretty straightforward. And then for the second part, the uniform convergence on the disk. Well, you say, well, look, right. So proving. Right, to prove uniform convergence, so on z less than or equal to rho, right? Well, since rho is strictly less than r, we have that summation. We have summation c sub n rho to the n converges, right? By what we just showed. Right, we just showed that we have absolute convergence in the full disk. So certainly, if we take it at this point rho, we've got absolute convergence. Right, but then c sub n, since absolute value z is less than rho, we know that summation. We know that c sub n z to the n is less than c sub n rho to the n, right? And so we can use the Weierstrass M-test, right? Because we have that each of the functions, right? Each of these functions is bounded, right, by this, right? And the sum of these bounds is finite. Right, so Weierstrass M-test tells you that this series converges uniformly. Okay, so by Weierstrass M-test, this thing converges uniformly. Okay, everybody okay so far?
So we only need the M-test to show uniform convergence.
That's right. Yeah, that's what you use the M-test for. Well, the M-test will show up a lot in this course. Everybody okay? Okay. So one of the homework exercises will be to show that. So the homework exercise for the ratio test, showing that you show that if this thing exists, if the limit of the ratios of the absolute value of the ratios exists, then that will give you the same thing as this. Okay. If it exists. Okay. And so you can use the ratio test also to determine the radius of convergence. Okay. Okay, I'm going to erase this. Okay, so one of the big theorems that we're going to go for today is the theorem about infinite differentiability of power series. Okay, that is that you can differentiate power series term by term infinitely within their radius of convergence. So that's what we're going to go do now. So this is term by term differentiation. Differentiation of power series. Okay, so here we go. So you have some function, and it has a power series expansion, a sub n, c to the n. Then, when f is holomorphic on its disk of convergence, it's holomorphic on its disk of convergence to the derivative has the power series expansion that you get by differentiating the original power series expansion term by term. Okay. And 3, f prime has the same radius of convergence. As f. Okay, so the hard part is this middle part, showing that the derivative is this term by term. It can be obtained in this term by term way. So that's let's go for that. Okay. This last part showing that they have the same radius convergence. Just apply the root test, and then you see that it's the same. So I'm not going to do the last one. Okay. So, okay. So they have the same. It's easy to see that they've got the same radius of convergence. So, okay. So here we go. So let g of z be the supposed power series expansion of the derivative. This is what we're hoping will be the derivative, right? And so what we want to do, right? We want to show that for any point z naught within that disk. So let's say that that the radius of convergence is r. We want to show that for any point within that disk of convergence, that of course that the limit of f of z naught plus h minus f of z naught over h minus our supposed derivative is 0, right, as h goes to 0. Right? That's our goal, of course. Right. This is our what we're hoping the derivative is going to be. So let's see that actually the derivative actually converges to that. Okay. So we want to control, as we always want to do, we want to control things, right? That's what we do in analysis. We control the size of the things. So what we're going to do is we're going to break up. Let's write f of z as in 2 parts, right? So we're going to break it into 2 parts, the sort of a polynomial part and then the tail. So this finite part first, we're going to call it a sub n. And then the tail from n plus 1 to infinity. Okay. So we have this polynomial part, and then we have the tail. Okay. And we're going to call those following signs, Sn and E sub n. Okay. So now So we have our radius of convergence R. We have some point z0 inside that disk, and we're going to take a little r that's that z0 is inside of. So little r is smaller than big R, right? So choose little r such that this is smaller than r, which is smaller than big R. Okay, so, right, so now let's consider this thing, f of z0 plus h plus f of z0 over h minus g of z0, and choose, let h be small enough that z0 plus h in size is also smaller than r. Okay, so h is z0 plus h is also inside this inside disk here. Okay, so now we're going to play this sort of the usual game of adding and subtracting the same thing. So we say, okay, let's right. So this z0, this is going to be Sn z0 plus h plus e sub n z0 plus h minus S sub n z0 minus e sub n z0, everything minus g z0, right? And then we're just going to group terms. So we group the Sn's together, Sn z0 plus h minus Sn z0 over h. We subtract off Sn prime at z0 and add it right back on. Then, so we've got the minus g of z0, and we also still have the tail part. Okay, so we throw in a zero, right? A cleverly chosen zero. Okay, and what we're going to do is we're going to think of this thing as these three differences. Okay, so I'm going to call this one number 1, this one number 2, and this one number 3. Okay, and we want to see that the size of, we can make the size of that as small as we want. So okay, so what do we want to do? Given any epsilon, right? We want to show that given any epsilon, there exists a delta, such that if the size of h is smaller than delta, then then the size of that thing is smaller than epsilon, right? Then the size of this thing, right? The size of the circled thing is smaller than epsilon, right? And then we break the circled thing into these 3 parts, and we're going to control each of those 3 parts. Okay, okay, pretty typical analysis stuff. If you, as you probably know. Yeah. Okay. So okay. So so the first part, dealing with number 1 is easy, right? Because S prime is just this is a finite sum, right? This is our S sub n, right? When you differentiate this finite sum, of course you can differentiate it term by term, right? It's a polynomial, right? So and you're trying to show that thing converges to this, but these are just the partial sums, right? These are just the partial sums of this. So of course these are going to converge to this, right? So we don't have to worry about that part, right? So basically by definition of a series, right? S of n prime S of n prime is going to converge to G, is going to converge to G, right? So we know that there exists some n naught such that if n is bigger than n, then the distance is smaller than epsilon over 3. So. Everybody okay with that? Okay. That's just the definition of a series, right? Okay. So let's do part 2 next. Part 2 is the kind of tricky part. So you say, well, okay, let's look at this thing, e sub n z naught plus h minus e sub n z naught over h. Right. Right. So that's these tails. Right. That's these tails here. Right. Now each of those converges absolutely at z naught plus h and at z naught. Right. Because the full series. Right. We've got convergence. Right, the radius of convergence is r, and z naught and z naught plus h lie within that radius of convergence. Right, so each of these things is going to converge, and so we can combine them together into one series. Right, it's legal to just write them as one series. So we can write as n plus 1 goes from there to there. Right, so we get a sub n. A sub n times z naught plus h to the n minus z naught. Sorry, it's kind of cluttered here. Right. So this is going to be summation a sub n z naught plus h to the n minus z naught to the n over h n plus 1 to infinity. Yes?
Pardon me, is that to see there exists an n naught such that n is greater than n naught?
Thanks. So we get this thing. We're gonna write it like that. Okay, and so if we're looking at the magnitude of that, right, that's controlled by summation and then this magnitude, z naught plus h to the n minus z naught to the n over h, something, as we go from n plus 1 to infinity. Right. Okay. And okay, so at this point we play a trick, which is that whenever you have a difference of powers, you can write that as a minus b times a to the n minus 1 plus a to the n minus 2b plus a to the b n minus 2 plus b to the n minus 1. Right. So this is kind of a typical trick that one plays. Okay, right. Whenever you have a difference of powers, right? So here we've got z naught plus h to the n minus z naught to the n, right? So we can write this z naught plus h to the n minus z z naught to the n as h times, right, z naught plus h to the n minus 1 plus z naught plus h to the minus 2 times z naught plus z naught to the n minus 1. Okay. So, right, and then, right, each of these things is smaller than little r in magnitude, right? Right, z naught plus h, remember, z naught plus h and z naught, we're all smaller than little r, right? So we can, if we're looking at the size of this, right, then we see that it's smaller than h, and we get r to the n minus 1, and we get it n times, so n r to the n minus 1. Right, and so what do we get? We get that this thing, we can get it to be controlled by summation this divided by h, we get n r n minus 1. Right, as n plus 1 goes to infinity, from n plus 1 to infinity. Right. And right, now this thing here is the tail end of a convergent series, right? Because remember, you know, our term by term differentiated series, you know, converge within the same disk, and so it's going to converge at little r. Remember, little r is inside that disk. Right. So if we sum this from, you know, 0 to infinity, that's a convergent series. Right. So it's the tail end of a convergent series, which means that we can, you know, given control of big N, we can make this as small as we want. Right. As big N goes to infinity, the tail must go to 0, right? For the series to be convergent. Right. So what does that tell us? That we can make this thing as small as we want. Right. So there exists, so since summation this thing converges, there exists an n1 such that if n, let's say capital N, is bigger than n1, then this term, the tail, is smaller than epsilon d to the k. Okay, so, right, so there's an n naught past which we've got control over the first term. There's an n1 past which we've got control over the second term. Okay? Yeah, okay.
Could you explain again why the series from n plus 1 to infinity of an n r to the n minus 1, why that is so convergent even though we're multiplying by 9?
Remember that we started off with this guy, right? And this guy converged within the disk of radius capital R.
Yes.
And we also were looking at this guy. And that also, if you do the root test on it, converges within the disk of radius, also the same R. Little r is bigger than big R, so we just put in little r here. This value is a finite value, right? That's it.
Gotcha. Okay, thank you.
Sure. Okay, so so now there's only one term left. Remember what our last term was, right? So the last thing was, so remember what 3 looked like. 3 was S sub n z naught plus h minus S sub n z naught over h. minus S of n prime at z naught. Right? Okay. Okay. And so we're trying to control this, the size of this, but right as h goes to 0, right? So for n bigger than either of n1 and n0 and n1, we want to see that we can make this thing small. But of course we can make this thing small, right? Because S of n is a polynomial, right? And this is the difference quotient where the limit of this as h goes to 0 will be the derivative, right? Polynomials are differentiable, right? So we don't have to worry about this, right? So since S of n is a polynomial, right? It's differentiable at z naught, right? We know that there exists a delta such that if absolute value of h is smaller than delta, then this thing this thing minus this is smaller than epsilon over 2. Right? Because this thing's a polynomial, so as the limit as h goes to 0 of this is this, right? So by definition, right, we can find a delta so that if h is smaller than that delta in magnitude, then this difference is smaller than epsilon over 3. Okay. So, right, what does that give you? That gives you that, right, altogether, that gives us that, the distance between, right, that we can find. So we can find a delta such that if h is less than delta, then this minus this is smaller than epsilon. And in other words, the limit of this is this. So it is differentiable, and the derivative is the term. It can be obtained as the derivative has can be obtained by termwise differentiating the power series. Okay. Any questions? Yeah.
So you mean the part 3 of this theorem,
Yeah.
the f prime has the same radius of convergence, that's just the root test, right?
Yes, that's just the root test. Yeah. Okay. Okay. So the corollary is, of course, that any power series is infinitely differentiable. Infinitely differentiable on its discrete convergence. Right, and you get it term by term. Right, and the derivatives are obtained via term by term differentiation. Yeah.
So, going back to part 1 of the
Yeah.
want to show,
Yeah.
that's supposed to be S prime sub lowercase n?
Yes, thank you. Someday I'll get through a lecture without making typo errors. I doubt it. Okay. Okay. So any power series, any function with a power series expansion is infinitely differentiable. There's this definition of analytic, right? So analytic just means that you have a power series expansion. Okay. So what we've just shown is that So I assume you all saw this term when you read the book. Analytic means that you've got power series expansion. What we've just shown is that analytic implies holomorphic. Okay, and then later on we're going to see that the opposite is true. That if you're holomorphic, then you're also analytic, right? And so that means that if you're holomorphic, then you're infinitely differentiable. If you're once differentiable, then you're infinitely differentiable, right? Which should be kind of shocking to you, because that doesn't happen back in where we came from. Yes?
What fact about complex differentiation makes that true?
It's the Cauchy-Riemann equations that the function has to satisfy this, basically like a differential equation, right? A set of partial has to satisfy a partial differential equation condition, right? And so that basically binds your function so much that it's well behaved, right? Yes.
But it is also like a stricter condition than like a real analytic function is not necessarily always a complex analytic.
That's true. That's true. And real analytic does imply that you're infinitely differentiable, right? So this, right? Yeah. So this doesn't.
But I meant like an analytic function on R2 is not necessarily an analytic function on the plane.
That's true.
Yeah. Right.
Yes, that's true. Yeah. Okay, so I'm going to skip some material, this business of integration on curves, because I think you should all be able to read that, right? Let me just sort of sketch out let me just write down a couple of things let me just highlight a couple of things. So first off, but I don't want to just get up and give a bunch of trivial definitions that you can all read. You can definitely do that. You don't need me for that, right? Okay, so integral over a curve. So right, you have some gamma smooth curve. You have some parametrization. Z, right? You have some parameterization, and you have a function that's continuous on that curve, right? Then, as you know, the integral over that curve is going to be the integral from a to b of f of z of t, c prime of t, dk. So this should be pretty familiar to you from basically calculus. Okay. Other things that we're gonna need. The length is defined as the integral of the speed, right? So over that time interval, we'll need a triangle inequality that the magnitude of the integral is controlled by the supremum of the absolute value of the function over the curve times the length of the curve. And we need fundamental theorem of calculus sort of thing. So that if you have an open set omega and you have a function that's continuous on omega, and that function has a primitive, that's to say an antiderivative, and the same thing as antiderivative, little f, then sort of obviously if you integrate, if you have a curve, so you have some set omega, and you have some curve gamma going from gamma A to gamma B inside of omega, then the integral of little f over the curve is the same thing as if you evaluate the difference at the endpoints of the antiderivative. Right? So the proof is exactly the same thing as the proof just uses the fundamental theorem of calculus, right? And the chain rule. I mean, the proof just uses the chain rule. Sorry. Okay. And so what this gives you corollary is that if little f has a primitive, then the integral over any closed curve is 0. Okay. If gamma is closed. Right? Because the endpoints are identical. Right? So you're just going to get the difference at the same point. Okay. So now let's get to the real stuff. We're going to show that this theorem of Cauchy Goursat. And this theorem basically underlies a lot of the theory from here on in. I remember back in graduate school when we were preparing for our exams, it was just like, you can prove everything by using this theorem. So just start from here, and then you can prove almost every other result that you need. Okay. Yeah. Okay. So here's the statement. You have omega, an open set in complex plane, and you have delta naught, a triangle inside omega. So delta naught is a triangle with interior in omega. Okay. So I should say delta naught is contained in omega, and it's a triangle with its interior in omega. So you have some set. It's an open set omega. And then you have some triangle inside there. And there's no hole, right? So omega doesn't have a hole, like, omega isn't a set like with a hole, and then you have some triangle that goes around the hole. So you want to avoid that sort of thing. There's no hole of omega that lies inside the triangle. Okay. So then, if f going from omega to c is holomorphic, then the integral over the triangle is 0. Okay, and so that means we take a parameterization of this edge here, and when you integrate along that path, then you get 0. Okay. Okay, so proof of yes.
Is there a reason it's a triangle, not just any polygon? Or is it just that?
It's just you can get to the polygons from the triangle. So we're just gonna do it for triangle, and then from there on you can go crazy. Yeah. So no, there's no reason. Yeah, so this is sort of like the first case for this theorem, and then there are lots of different statements of the theorem, like pushing how far you can go with that. Yes.
How is this different from like the thing about the closed curve, where you take the integral along that, then that is equal to 0?
So you don't know that this thing has a primitive, right? It's just a holomorphic function. we will see that it does guarantee a primitive. Okay, but at this point we don't know that. Yeah. Okay, so here's what we're going to do. Okay, so you start off with your triangle delta naught. Okay, and it's oriented. It's given this positive orientation. Okay, and what you do is you divide each side diagonally. So divide each side in half. Okay, divide each side in half, and you create these subrectangles. Right. I'm going to call them dyadic subrectangles. Okay. Okay.
Sub like rectangles or triangles here?
Sorry. Subtriangles. In I probably said dyadic subrectangles hundreds of times for other proofs. Yeah. Maybe I should have just done this with rectangles, but you could do this with rectangles. Anyway, yes, you're right. Triangles. Thank you. Yeah. Okay. So dyadic subtriangles. Right. So you've got the mother triangle, right, and then you've got the child child triangles. Okay. And you notice that the integral over the big one, right? If I go like this, that's the same thing as if I take the sum over the paths for the sub guys. So I'm going to call the sub guys delta 1. Just for now, I'm going to call them like this. Okay, delta 1 with I sub I. I goes from 1 to 4. Okay, right? Because when you go over the little guys, 1 like this, you get this, but then you get this, and you get this, right? And then these will cancel out, right? Because you're going in opposite directions. So these integrals will negate each other, and you're just left with the sum over the outside. Okay, right? So you know that this this is equal to the sum over the integrals over the small guys, right? Right. In particular, you notice that this is the same, and that this, by the triangle inequality, is smaller than the sums of the sizes of these integrals. Okay. So you create a sequence of subtriangles such that the integral over the next stage is bigger than a quarter of the previous stage. Yeah. So, sorry, that's the right thing to say. Right. So this is our delta naught. We're going to choose a delta 1 that has to eat up a quarter of the integral of the original. Right. Right. If they're all smaller than a quarter, then you get the contradiction. I'm sorry, I was crazy. Yeah. Thank you. Okay. Okay. So yeah. So okay. So you create this series of subtriangles. Does it make sense now? Now that I've actually said something correct. Yes. Yeah.
The notation you have delta sub I in that bottom part, is that referring to like the generation of the triangles?
Okay.
Or is that-
Yeah. So here's what we're going to do. Sorry. So you start off with your delta naught. Okay. You do the dyadic subdivision. Okay. At least one of these child triangles has to have this condition true. Right. Choose that guy. Okay. Choose that guy. Call it delta 1. Okay. Then iterate. Right. Keep on going. At least one of these guys must take up a quarter. Must eat up a quarter of the original. Right. And so call that guy delta 2, and so on and so forth. Right? So on and so forth. Okay, sorry. Okay, so okay, so you end up with this series of this nested series of triangles, right? That that such that they satisfy this condition. Right? So note that the integral over the 0th triangle is controlled by 4 to the n of the integral over the nth triangle. Okay, and so what we're going to do is show that this term on the right-hand side can be made as small as we want. Okay. Okay. So we'll control this. Okay. So okay. So notice that. Notice also that the the intersection of all the triangles is a single point, right? If we take the integral, over we've got a nested sequence of compact sets, and their diameters are going to 0, and so when we intersect them, we end up with a single point, and that point we'll call it Z0. I see I'm being kind of sloppy here. I'm not really distinguishing between the boundary of the triangle and the triangle itself. I should probably put boundary signs here. We put boundary signs to indicate that when we're integrating over the boundary, and when I'm taking this intersection, I'm intersecting the planar object, planar object, the triangle. Okay, so we want to get control over that thing on the right, and the trick is to do a linearization. So let me just keep an epsilon in mind here, and we're going to linearize f at z0, right? We're going to write f of x at f of z as f of z0 plus f prime z0, z minus z0, plus, right, some term that the error term, right? So eta z minus z0, where the limit as z goes to z0 of eta z is 0. Okay, so this is just by the definition of holomorphicity. So choose a neighborhood around Z0 in which eta is smaller than epsilon. Okay. Okay. Now choose n large enough that that the diameter of the nth guy is smaller than delta. Okay, so right, Z0 is the point that you get by intersecting all the triangles, right? And we have this delta neighborhood in which eta is small, right? So eta is small here, right? And we choose we go down far enough along the list of triangles that we find a triangle that lies entirely inside this disk, right? So just choose it so that its diameter is smaller than delta. Okay, so then that basically does it for us. Then if we look at the integral over this nth guy and use the linearization, well, we get the integral over this thing of f of z naught plus f prime z naught z minus z naught plus a to z z minus z naught dz. Right? But this is just a constant, right? This is just a constant, and we're integrating it over a closed curve. The constant definitely has an antiderivative, right? So the integral of that is 0, right? This is just a linear term. The linear term also has an antiderivative. So the integral of this thing is 0, right? So the only thing that survives is the integral of the error, right? So we get that this is going to be equal to, right, the integral of the error. So you take this, you intersect everything, you get this point, you take the linearization at that point, and then you notice that if you integrate, you just get the integral of the error because because the line is, this line is it has a primitive. Okay. So then we invoke triangle inequality. Right? But eta, remember, was smaller than epsilon, and so we get this is smaller than epsilon. Now z minus z naught is smaller than the diameter of so this way. If you have 2 points z and z naught, then the distance between them is smaller than half of the perimeter of the triangle. Okay. So maybe that's an exercise if you want. Okay. So what do we get here? We get this thing is smaller than epsilon. This thing is smaller than the perimeter of the nth guy divided by 2, and then times this thing, right? But times this thing. But this is the length. This is the length of the curve. This is just the perimeter of that triangle, right? So we get epsilon perimeter squared over 2. Right? Now, when you the perimeter of the nth guy is equal to 1 over 2 to the n times the perimeter of the zeroth guy, right? Because at every point we took this dyadic thing, right? So the perimeter is going to be half at every point. At every stage, you decrease the perimeter by half, right? So what's this? This is epsilon over 2 times the original perimeter squared over 4 to the n. Okay. So what does that give you? That gives us, coming back here, that gives us that this thing is controlled by epsilon over 2. This thing is controlled by epsilon over 2 times the original perimeter squared. Right? And so what does it tell us? That we can make this thing as small as we want. Right? Whatever epsilon we have, we can make this thing smaller than that epsilon. Okay, so this is 0. Okay. So, and it's kind of nice, right? The proof. There's only two parts to this proof, right? One, creating the dyadic, creating the dyadic subtriangles, and then two, and then using their intersection to get the point, and then two, using the linearization, because it's holomorphic, you've got the linearization, and then when you integrate the linearization, you notice that these parts just vanish, right? And so what you're left with is the integral of something arbitrarily small. Okay, here we go. So I made a mistake at the end of the proof of Cauchy Goursat, and I just want to correct it here. So you remember what we were doing was we had that sequence of nested triangles, right? And then in the limit, if you take the intersection of all those triangles, you get this point z naught, right? And then you you linearize f at z naught. So you write f as z naught plus f prime at z naught, z minus z naught, plus some error, right, where eta goes to 0 as z goes to z naught, right? And remember, what we wanted to get was a bound on the integral of f over the boundary of some tiny triangle delta sub n, right, where you had fixed an epsilon, and then you'd chosen the delta sub n so that on the boundary of the triangle, epsilon was smaller than, eta was smaller than epsilon, right? That was the thing, right? So delta sub n was chosen so that eta was small. Eta was small there, right? And so then our game was use the linearization, right? So you say get that this thing is equal to this. So this was pointed out. I forget by who, but one of you pointed this out at the end of class after most people had left. Right. So we wanted to get some bound on this, right? And the point was that because this thing this thing has an antiderivative, the integral over this closed loop was 0, right? And so we thought we're only left with this thing. We were left with this thing, right? And it's at this point we want to apply the triangle inequality for complex integrals, right? Which says that that this integral is controlled by the supremum of the absolute value of this over the supremum of the absolute value of this as z ranges over the curve times the length of the curve, right? So I wrote up something that was wrong last time, but I wrote something like this is less than I did something anyway. I wrote up something wrong. It should have been we should have used the triangle inequality at this point, right? And then the point here was that eta is smaller than epsilon. This distance was smaller than the perimeter divided by 2, and then this distance is the perimeter, right? So you get this, right? And then we showed that that times anyway, we showed that could get arbitrarily small. We could make things arbitrarily small. So anyway, so that's the right way it should have been written. Okay, and that gave us the proof of Cauchy Goursat that we could that whenever you have a holomorphic function, you're integrating over this, the boundary of a triangle, you get 0. Okay.